So hello guys and welcome to another video. So in this one, we are going to be looking at the solution to March 2024 as a paper. So again, this is not going to be a solution video as such, because if you guys have been taking the live sessions with me so far, maybe this year, so you know that usually I solve everything in class. But because now we are so close to the exam, you guys have a lot of prep, obviously. So now I feel that it's better that just to save time, I solve it beforehand and then I'll just go over the solution with you. So this is going to be a walkthrough video. So it's not a solution video per se, because I won't be solving it right now. So March 2024, at the time of the making of this video, this is the latest AS paper available to us for practice. So obviously it's going to be great in telling us the type of questions that can come up, and it's also going to be great for your practice. You can also use this to gauge your time management skills and so on. So March 2024, let's get right down to it. All right, so 1A, table 1.1 lists some SI quantities, and you have to complete the table by indicating with a tick which ones are SI based quantities. So do take care that these are not units, these are quantities that you need to indicate. So current is a base quantity, energy is not a base quantity, force is not a base quantity, mass is a base quantity, right? So for example, if even instead of energy, let's say if maybe amperes was written, this is where I would not place a tick, right? Because that's a base unit, not a base quantity. Why I'm telling you this is because questions like these have come up in the past, and students do tend to make mistakes with those. Part B, use the definition of power to determine its SI base units. Again, this is really straightforward. Power is work done over time or energy over time. Work done I write as force times displacement over time. Force I write as Newton's second law, mass times acceleration. And then you have the displacement over time again. Mass is in kg, acceleration is meter per second square, displacement is in meters, and time is in seconds. So meter times meter would become a meter square. And this S, when it comes up, this would be subtracted as well. So this would be -2 -1. So kg meter square per second cube is what we get. A light meter is used to measure the intensity of light in a classroom. Daylight is incident normally on the sensor of the meter. The sensor has an area of 2.2 centimeters square. So this is not a SI unit, right? Reading on the meter is given 950 watts per meter square. Calculate the power of the daylight incident on the sensor. So I know the intensity formula is power over area. I got to know of this because the word intensity was used in the question itself. So power is just going to be intensity times area. Intensity is given in SI units. However, this is per meter square. This is cm square. So I need to convert the cm square to meter square, because I can say that 1 meter is 10 to the negative 2 centimeters. So then I just square both of these to get the conversion between meter square and centimeter square. So to convert centimeter square to meter square, oh, I guess I messed this up. This is meters. This is centimeters, right? So I just square both of these, and then I get 10 to the negative 4 as the square of 10 to the negative 2. And then I just go on and find the answer, which is 0.21 watts, correct to 2SF. Next part. 2A, define acceleration. Rate of change of velocity, you guys know, is my preferred definition. If you guys want to write this, you can also say change in velocity over change in time, but that's just about it, right? You just can't say velocity over time. That would be wrong. An Olympic diver stands on a platform above a pool of water as is shown. When the diver is on the platform, his COG is a vertical height of 9 meters above the surface of the water. So this COG is 9 meters above the surface of the water. And the diver jumps from the platform with a velocity of 5.9 meters per second. This is at an angle, as you can see. At an angle of 60 degrees to the horizontal, air resistance is negligible. When the diver hits the surface of the water, his center of gravity is a vertical height of 1.2 meters above the surface of the water. Calculate the speed of the diver at the instant he hits the surface of the water. So I'll just go through my solution in a while, but I just want you guys to also know that there could also be an alternative solution here, as opposed to what I've done. Some people, when they first see this velocity as should happen, the first thing that comes to their mind is projectile motion. You could have also used projectile motion to do this question. Splitting this up into components, this one would be the sine component since it's not with the angle. This one would be the cos component. So once I know the vertical component, which is 5.9 sine 60, then using the equations of motion, I can calculate what its what his final velocity would be when it is this distance below, right? So that is also another thing that I could use because I need to find the speed of the diver when he hits the water. That is one way. I did not do it because I felt that it would be too much work. Because I would have to do everything for 5.9 sine 60 first of all. But remember that the answer that I would get in that case would also just be the vertical velocity. And then I would need to use the resolution again to find the total velocity because this 5.9 cos 60, this would be there and there would be the vertical component and then I would need to find the resultant like this, right? So what I used is the conservation of energy. So initially the diver has kinetic energy and he also has potential energy. Now, if you read the question, everywhere there was a reference to the center of gravity being a certain position. So the idea regarding potential energy is this. This is also covered in my lectures. Is this idea that whenever you talk about the potential energy of something, if you look at your syllabus, there's the term written like this, that EP, actually it's written like this, delta EP is mg delta H. So delta H is the change in height. Now that change in height could be according to any point. So for example, if I'm talking about the diver, I could take the tip of his hands, I could take the head, I could take the feet. All the examiner is doing here is that he's talking about it with reference to the center of gravity, right? So the center of gravity was initially 9 meters above. Now it's 1.2 meters above when he just hits the water. So the difference in height is really what we are concerned with, right? Which is 7.8 meters. So here he has kinetic energy. He also has potential energy. And at this point, he would not have any potential energy because this is the lowest point. This is really where we are measuring the heights with reference to. So I just use the idea that the loss in potential energy, because he's losing this height, would be equal to the gain in kinetic energy. So this is what I use. But again, I'm not just going to write half mv square. I'm going to write half m v square minus u square because he did have some initial speed, which is going to lead to some initial kinetic energy as well. Do keep in mind that it's v square minus u square, not v minus u squared, right? This is wrong. It's the difference of the squares, not the square of the difference. So the initial velocity was 5.9 v. The final velocity is what I need to find out. This is that mg delta H expression. So here, this mass is missing. Oh, the mass is not missing. Yes. Now you also know this, that the masses would be there in the kinetic energy equation as well as the potential energy equation, and both of these masses cancel out, right? So even before going on to your calculator, first just try to look at the expression and make sense of it. The mass was not given here. And the very simple answer to why it's not given is that it's not required, right? So I have G, I have delta H, I have this entire thing. From this, I just need to make V the subject of my equation. So V squared turns out to be this. V turns out to be 13.7 something, I guess. And when you round to 2SF, you get 14 meters per second. All right. Diver in B enters the water and decelerates. So deceleration we know is the name given to the idea that when you lose speed. Describe and explain the variation of the viscous drag force acting on the diver in the water as he moves downwards. Now, as he moves downwards, this means that he's going down, and like any resistive force should act, the resistive force is going to be upwards, right? Here, it's not really even required, but it's just good to think about it because we don't know, maybe it could be asked in a later part. So since he is decelerating, his speed is decreasing. And because his speed is decreasing, the viscous drag would also decrease. What I've written here, this is just supplementary stuff, but you don't really need to talk about this. Just this first line is enough. The diver has a volume of this much, density of the water in which he is this much. Show that the upthrust acting on the diver when he is entirely underwater is 740 Newton. So you know that this equation that we have, U equals to rho g delta V. So delta V is the volume of this object that we're talking about, which is going to experience the upthrust. How much of it is below the water? Because he is entirely underwater, so I'll take this entire value in this calculation, right? So I calculate this, turns out to be 735.75 to 2SF. This is 740 Newton. All right. At a particular instant when the diver is entirely underwater, his horizontal velocity is zero, right? So horizontal velocity is zero, it's at rest. He's just going to be moving vertically. Viscous drag force acting on him at this instant is 950 Newton vertically upwards. That is what I have marked in this diagram, where you have basically, I don't know, maybe this guy is Bob the Builder. I haven't watched the cartoon in quite some time, but 950 Newton, this is upwards, and the diver has mass this much. Determine the magnitude and direction of the acceleration of the diver. So I have 950, which is upwards. The viscous drag, as we just said, here it's given as upwards, but usually we know that whatever direction something is going in, viscous drag is going to be opposite. So it does depend on how something is moving. However, the upthrust that we calculated, that's always going to be upwards, irrespective of if the diver was going up or going down. It's always going to be upwards. Similarly, the weight is always going to be downwards, right? So using W equals to mg, I find out the weight, which is 765. Just looking at this, I can see that 950 plus 740, this is more than the downward force, which is 765. So resultant force is upwards, right? Because F up is greater than F down. Newton's second law tells us that whatever the direction of the resultant force, the acceleration will also be in that direction. So even before going on to the calculation, I write here that the resultant force, and hence the acceleration is also upwards. Then I use Newton's second law. So 950 plus 740 upward forces minus the downward force 765 equals ma. So 78 times a. A exactly turns out to be this. So to 2SF, this is 12 meters per second square. Question number 3. A thin metal wire of diameter 1.2 into 10 to the negative 3 meters is used to suspend a model planet as shown. Then you have the variation with stress for wire X, which is shown in 3.2. Let's just focus on this line for now. Do look at the axis. The stress is in gigapascals and the strain is in a multiple of 10 to the negative 3. The strain in X is given as this. Use 3.2 to calculate the force exerted on the wire by the model planet. So if I do have the strain given, I can just read off what the stress is corresponding to this value. Right in the middle is 0.7. This is one box after that. So that's 0.72 gigapascals. So now that I know the stress, I also know how stress uses the force in its calculation. So stress is force over area. I was given the diameter at the start of the question, so I can find the area using this equation. So F would then be stress times area, and then you just multiply the two. Area is given by pi d square by 4 for a circular cross section. So just find that out, multiply, and this is the answer I get. Elastic potential energy of X is 0.31 joules. Calculate the original length of the wire before the model planet was attached. Since I am given the elastic potential energy, I can find out the force corresponding to that, right? So I have half Fx, and all right, so this part A was generic to both of these parts. So for the strain, whatever force I found out is going to be used now in part 2. So I have force is 810, and I can find out the extension. Extension turns out to be this. I was also given the strain. What is the strain by definition? It's the ratio of extension to the original length. Now I know the extension, I know the strain, so finding the original length is very straightforward, which turns out to be this. This is what was required. So this, in my opinion, it's not really a difficult question, but I would just say a different question to the ones which are usually asked. Wire X is replaced by a new wire Y with the same original length and diameter, but double the Young modulus of X. Wire Y also obeys Hooke's law. On 3.2, draw a line representing the variation with strain of the stress for Y. So if I think about the Young modulus, that is FL over AX, L is the same, and diameter is the same, so A is also the same. So I really have differences in the F versus X part of the Young modulus. Now it's double the Young modulus. If you want to think about this in the context of graphs, so you know that we had a stress strain graph above, right? So if the Young modulus is double, this means that really the gradient of this graph would also double, right? Because the gradient of a stress strain graph for the linear part is the Young modulus. That's one way to think about it. The other way to think about it is this, and it's also in a way linked to graphs, is that now since I have double the Young modulus, I can say that for the same strain, I now have twice the stress, right? For the same strain, I now have twice the stress. Look at these numbers here. So if this is double, this means that this entire fraction is double. And one way to look at it is to say that for the same denominator, the numerator is now double. Now, when I want to make the graph, because I know that the strain is this much, I can also say this, that for the Young modulus to be twice, I can also say that for the same stress, which are used in a calculation, the strain is now half, right? If I write it like this, same strain, but now same stress, but now half the strain. So this also gives me the same idea that it's 2 times the Young modulus. All of this is the Young modulus. So same stress, but half of 5.4 is 2.7. So my graph should still go from the origin and pass through this point, and this is the graph that I get. Just try to correct this a bit. So yeah. Question number 4, a nucleus P undergoes alpha decay to form Q. Complete the equation for this decay. So you use the conservation of nucleon number, conservation of proton numbers. Alpha, you know, is 4, 2. And after you have this, you can see that this should be 4 less, which makes it 211. This should be 2 less, which makes it 82. Principle of conservation of momentum, the simplest statement for a closed system, or instead of this, you can say, if no external forces act, then you can write the total momentum remains constant. Or if you don't like this, you can also say the sum of the clockwise moments equals sum of anti-clockwise moments. Both are acceptable. Before the decay, nucleus P has a speed of 3.2 into 10 to the 5 meters per second. After the decay, nucleus Q is stationary. Calculate the speed of the alpha particle after the decay. So this was our nucleus P, which was initially moving at this speed. Then it breaks apart. The one in blue is Q, which is now stationary, so it's not moving. And we know that the alpha particle obviously should move by conservation of momentum, and we need to find out the speed v. So total momentum before should equal total momentum after. Total momentum before, mass times the velocity. So 215u times this velocity, which is what's written here, equals 4u times v, right? There's no q here because it's stationary. Again, always first write out the expression before jumping onto the calculator. Remember that it's the machine and you're not the machine. So you tell it what to do. Now, why am I saying this is because here you did not even need to convert this u here. So don't just pick up your calculator and start to convert, uh, start to multiply this by u, because you didn't even need to convert this here. If I look at this carefully, I see on both sides the u will cancel out anyway, right? So I didn't even need to go to the formula sheet. I just make v the subject here, which is this, and to 2sf, that's equal to 1.7 into 10 to the 7 meters per second. By reference to the direction of propagation of energy, state what is meant by a transverse wave. Again, do pay a lot of attention when the examiner says by reference to this thing, because usually we know that for transverse waves, I could say two things. I could say particles vibrate perpendicular to direction of propagation of energy, or I could also say this, that it's perpendicular to the direction of wave motion. Both are correct. But if you wrote wave motion in this part, you would lose the mark, because the examiner explicitly says that explain this to me with reference to the propagation of energy, right? So here you had to use the word propagation of energy. A space telescope is designed to detect EM radiation with wavelengths in this range, so 12 micrometers to 28 micrometers. If I look at the orders of magnitudes, so this is basically 10 to the negative 5, which is just slightly larger than visible light, which makes it infrared. Part C, a detector on another space telescope detects an EM wave. Signal from the detector is transmitted to Earth and displayed on an oscilloscope as shown. Frequency of the signal displayed on the oscilloscope is equal to the frequency of the detected EM wave. Time-based setting is given. Calculate the wavelength of the detected EM wave. So because this is an electromagnetic wave, this means you already know what its speed is supposed to be, right? It's the speed of light, 3.0 into 10 to the 8 meters per second. And because you're also given the time base, all you need to do is find the time period, and then you can use the wave speed equation. For the oscilloscope, remember that you don't need to memorize the formulas as long as you're good with units. Because you're going to find the time period, you know horizontally, this is what the time period looks like here, this entire thing. So the time base, you just multiply by the divisions here, by the distance here. So this is 5 into 10 to the negative 15. I just multiply them by the horizontal divisions, which in this case are these 6 boxes, which is also 6 centimeters. And I get this as the time period. Then, because I have the time period and to keep my calculation simple, I don't want to go to frequency. I just use this modified equation, lambda over t. And from lambda over t, I just make lambda the subject, just multiply the speed and the time. This is what we get exactly. All right, 6 part A. Coherent visible light of a single frequency is incident normally on a double slit. This produces a pattern of bright and dark interference fringes on a screen, which is shown. There are 7 bright fringes. Explain how the pattern of bright and dark fringes are formed. Again, this is a question which used to be asked a lot, uh, maybe like 5 to 6 years back, but now this is that type of question making a resurgence after long. They just want to know how these fringes are formed. So let's work from the ground up. You first have the light here, which passes through the double slit. The idea of the slits is to make the light diffract. So on passing through the slit, it's going to diffract, or you can say it bends. And both of these lights bend and they superpose, or you can say they interfere to give you that pattern, right? Now, the next thing you need to talk about is how do you even get those bright and dark fringes? So you know that at bright fringes, you have constructive interference happening. And I've written this according to phase difference. So phase difference is 0 degrees. So the waves basically meet in phase, causing constructive interference. Destructive interference is where the waves meet exactly out of phase. So the phase difference is 180 degrees, hence destructive interference. You could have also given this entire answer exactly like this, but in terms of path difference. In that, you would say that for constructive interference, the path difference is a integer multiple of the number of wavelengths. I'm talking about this idea, n lambda. And then for destructive interference, you would say it's an odd multiple of half wavelengths. All right. Do not use these symbols directly without explaining what each of these stand for. All right. So remember, again, I'm repeating this. N lambda, you can write in words as a integer multiple of the wavelengths. And destructive interference, you can write as an odd multiple of half wavelengths. Distance between centers of bright fringe X and Y is given. So if you look at the distance between X and Y, this is 1, 2, 3, 4, 5, 6 fringe widths, basically. So do not be misleaded by these 7 bright fringes. It's like if I show you my hand, so I'm not an alien or something. I have 5 fingers, but the spaces in between are 4, right? So here we had 7 bright fringes, but the spaces in between were 6, right? If you feel in doubt, just count them like I did. So this is 6 fringe separations, which is given as 10.2 millimeters. So I divide by 6 to get 1 fringe separation. Slit spacing is A, which is given. Distance from slits to screen is given. All I have to do is use the Young's double slit equation and find out the answer. The light is replaced by different visible light with a shorter wavelength. State how the new fringe separation will compare. So because lambda goes down, your X, the fringe separation will also go down, right? So you have less fringe separation. Part B, a stationary wave is formed on a stretched string AB as shown in 6.2. P, Q, and R are points on the string. On 6.2, draw a cross to show the position of a node. So anything at this zero displacement position, at the mean position, this is your node. So you could have marked A or B. State the phase difference between P and Q. So we know that in a loop between two nodes, all points are in phase. So there's no phase difference here. And the next part, the phase difference between P and R. So these are adjacent loops. In this case, they're exactly out of phase. So the phase difference is 180 degrees. 7A, define electric potential difference. Again, this is something we've been doing for quite some time now. Work done by a unit charge and moving through a component, or you can give the energy counterpart to this definition, which is that this is the electrical energy transferred per unit charge from electrical to non-electrical forms, right? That's what you would also write. Part B, a cell of EMF 1.8 volts, internal resistance R is connected here. Resistance is 6 ohm, filament lamp is shown. So this is shown in 7.1. The dotted lines show that this is the cell. So this is the internal resistance. And you have the 6 ohms resistor and the lamp here. Switch S is initially open. Ammeter reading is 0.25 amperes. So you know that in this case, the current is going to go like this, right? From positive here, because the switch is open, no current goes here. Determine the internal resistance of the cell. So I know the EMF of the cell. I know the current. So I can find the total resistance, which is just the EMF divided by the current. Turns out to be 7.2 ohms. Because this is a series circuit, so the resistance is the sums of these resistors, right? That's how we deal with resistors in series. So 6 plus R should equal 7.2. And from this, R turns out to be 1.2 ohms. Part C. At time t1, switch S and 7.1 is closed. 7.2 shows the variation with time t of the ammeter reading I. So previously, before the switch is closed, this is the current value as to what we just calculated, whatever this was. Let's write it down. So this was that 0.25 amperes. So at time t1, the switch is closed, and this causes the current to go like this. If you feel like you need to look at this carefully, and you do indeed, pause this video and have a look at it first. Just take like 10 seconds and look at the shape and see what you can observe. State whether the EMF of the cell after T1 is greater than, less than, or the same as it was before T1. So the answer is that the EMF is always going to be the same. In AS as well as in A2 physics, when we'll be talking about cells, we'll be talking about these as things that never run out. So the EMF is going to be the same. The next question here is the hardest question on this entire paper. You guys know that I love to do this, just so that you have an idea of what to spend more time on when doing the paper as a whole. So this is the hardest question here. By considering the effect of the lamp on the total resistance of the circuit, explain the variation of the ammeter reading shown in 7.2. So let's go back to the circuit. You know that if the switch is closed here, both of these would become a parallel connection. Do remember that whenever we talk about parallel resistors, if you have some resistor, I don't even care what its value is, you have some resistor. When another resistor is connected in parallel with that, the resistance will always go down. That's just how the math for it works out. Now, if I would say that, for example, if you ever have any resistor and you put in another resistor in series with it, if I would say that the resistance increases, you guys would be very well with that explanation. Similarly, it works entirely in reverse and parallel, that this resistance in parallel would go down, and as a result, the total resistance would also go down, right? This is the first thing I know. So the total resistance goes down, which also means that the current would go up, which it does, but only shortly. After that, you can see that the current is now falling again. For the current to fall, the resistance must be rising. But it's not like we have a variable resistor here or something. So what's happening here? The idea is that because we have a non-ohmic conductor here, this guy is what is making the resistance go up. Because you know that the current which goes through this part here, that is going to cause a heating effect. And because of the increased molecular vibrations, it's also going to cause the resistance of this to go up, right? So the total resistance would also be going up. This is the idea here. So the total resistance was going up. But I bet a lot of you did not notice another thing, which we don't know for now if there are marks for this or not. Only the marking scheme will tell. But there's also another idea here, which is that if you observe these lines, let's make these. If you observe these lines here, so this is what the initial current was. And you can see the current leveling off at another level. But this new current is more than this old current. What's the reason for this? Now look at this answer really closely. All of this we have talked about. So the lamp is in parallel, so resistance goes down, current goes up. But because of the heating effect of the current, the temperature of the lamp also uh, increases, right? Which causes the current to decrease. But the final current is still more. That's because of this reason that since the resistance is still lower than before, the current settles at a higher value. Let's say that this resistance, just for the sake of argument, it wasn't even 6 ohms. Let's say this is 6,000 ohms. This is 6,000 ohms. And I put in any resistor whatsoever here. Could be a value more than 6,000, could be a value less than 6,000. You know how it works is that the resistance in parallel is always less than the total, is less than the smallest resistor, right? So if, for example, if I put in a value 4000 here, the parallel resistance would be less than 4000. If I put in a value like 8000 here, the value would be less than the smallest one, which would be 6000. So overall, the resistance has decreased. Hence, the current is always greater than what it was before, right? So because of this in-depth analysis required in this question is why it won this award of being the hardest question on this paper. It was really conceptual here. All right, now easy stuff again. Last question, state the name of the class of fundamental particles that contain a neutrino. Neutrino, antineutrinos, electrons, positrons, all of these fall under the umbrella of leptons. A hadron has a charge of plus 1e. E is the elementary charge. Hadron P is composed of a down antiquark and only one other quark. So it's an antiquark and a quark, so I know that it's going to be a meson, right? By definition, that's what mesons are. Identify a possible flavor of this other quark. So if it's anti-down, I know that up, charm, top are positive 2 by 3e, which leaves out the others, which are down, strange, and bottom. These are negative 1 by 3e. So an anti-down would be the same charge, but just positive. And for it to make the total charge plus 1, you need another 2/3. So you could write up or charm or top, right? So all of these would be correct answers. Nucleus Q undergoes radioactive decay to form nucleus R, emitting an antineutrino and another particle X, as is shown in this decay equation. State what is represented by X. So this is an antineutrino. So you know this must be beta negative decay. So this is your beta negative particle, or if you want to write an electron, that's also fine. You know that in beta decay, nothing happens to the nucleon number, right? It's the same. But if you talk about the charges here, you know that the beta negative particle is this. So in this decay, the proton number increases by 1. So R has a greater charge than Q by 1. All right. So that's this entire paper. So hope you guys learned something here. And the reason I thought to do this is because the mark scheme of this, at least to my knowledge, it's not out yet. So you guys must be lacking an anchor for like really gauging your responses. So this is what it is. So best of luck, guys. Don't worry too much. Just do your best. Focus on what you can control. And yeah, so best of luck. All of us are counting on you. And then, inshallah, see you after your exams. Take care and goodbye.